Hello. In the previous class, we discussed about arbitrary solution of Stokes equations, and we have seen application of the complete general solution. Okay. And in particular, we discussed a lamp solution and also an optimal solution, which is in terms of 3 scalar harmonics. Okay. So, another interesting application is swimming microorganisms. So, we approximate it as a spherical object, but in reality you will see various other shapes, but there do exist various microorganisms which are really spherical in shape. So, hence the arbitrary solution that we have developed will be very much useful. Okay. But in today's lecture we discuss about some applications and then how a lamp solution can be used to understand the mechanism of swimming microorganisms. Okay. So, there are several variety of microorganisms. For example, one can think of artificial and some are natural. Okay. So, we try to understand the mechanism and how they really move. Okay. So, let us have a look at it. So, primary contributions in this direction have come from the pioneering researchers from Cambridge group. So, one is Lighthill and then John Blake. Okay. So, the concept of swimming microorganisms and its mechanics has been understood by Lighthill and very nicely explained in these articles with a term called squirming motion. Okay. And the basic idea of squirming motion is most of these microorganisms, they contain some hair like structure on the surface, and naturally once they are in the fluid, so the hair like structure will move. Okay. So, the motion which is generated by virtue of the movement of these hair like structure, so that is the squirming. Okay. So, now what is Lighthill's approach? Okay. So, when you say you have an object and then on top of it you have some hair like structures which are typically called cilia. So, by virtue of their movement, so the microorganisms will move. Okay. So, then what is the corresponding mathematical approximation, etcetera, have been very well explained in this. So, in today's talk we will summarize in a nutshell the key features and then also we summarize the corresponding mathematical model. Okay. So, if you see this is Lighthill's work, and it is mentioned that nearly spherical deformable bodies at very small Reynolds numbers. So, when it is mentioned nearly spherical deformable bodies, it could be the microorganisms are spherical, but it is nearly spherical because by virtue of these hair like structures on the surface and by movement of the hair like structure, the object appears as slightly deformed. So, the typical approach to model is something known as a spherical envelope model. This you will see what do you mean by spherical envelope model very soon. Okay. So, with this forewords we proceed to understand the mechanics of swimming microorganisms, and of course, we will see some examples. So, the basic question in this regard is what drives a swimming microorganism. Okay. So, and under what circumstances, when we say what drives, so we are not considering any external fields, like, so you have a steady flow not driven by any ambient flow, then you put a microorganism, still you will see it is able to move. Okay. So, what drives such microorganism? Lot of bacteria, okay, etcetera. So, the answer to this is one would say, suppose you leave some let us say some insect or something. So, immediately it will make some disturbance, right. So, if you have small wings, then it will try to do this and then you can see there is a movement. So, there is no external field which is driving the flow, but the movement of the wings of that insect, right. So, similarly, microorganisms without any external field, how it can move. Suppose there is an object which is let us say, if you put into some liquid, it gets deformed. So, then by virtue of its deformations, you will see suddenly there is some movement of the flow. So, the natural question when this is asked, naturally one answer to this is maybe by small deformation it can. So, now when it comes to the microorganisms, what are these small deformations? As I indicated, the small deformations are due to the movement of the hair like structure. Okay. So, that is the question, can a spherical deformable body swim at very small Reynolds numbers in the absence of any external force? This is very important. We are not considering any external force. By virtue of its structure, whether a microorganism can swim. So, the answer is yes, provided such a body can perform small oscillations, right. So, how this small oscillation can come? So, when it comes to real bacteria or microorganism, so there is a life in it. So, by virtue of that life there is some activity, otherwise you have to create some artificial spermats and then artificial microorganisms. So, that is also quite visible these days in various applications. Okay. So, in that sense the understanding mechanism of swimming microorganisms is very much essential. Okay. So, this is the answer. So, if it can perform small oscillations, right. So, let us see some examples. Typical example is called volvox. It is a green algae, and then they grow in colonies. So, they are made up of some flagellate somatic cells and a smaller number of germ cells that are embedded in the surface of a hollow spherical matrix. That means, so you have a spherical structure, then so depending on the environment, so these flagella structures will be developed and then they will be sitting on this spherical structure. So, you will see a picture very soon. So, this is mostly grown in fresh water. Okay. So, the cells swim in a coordinated fashion. Okay. So, you can see, so the picture is like this. So, this is from Professor Raymond Goldstein from University of Cambridge. So, he has nice experiments conducted on swimming of volvox. Okay. So, these are the colony of cilia, okay, that is a hair like structure. So, in each what you say this is magnified. So, they are collection of hair like structures and they will be moving. Okay. So, several of them as each one colony. So, they will be moving. So, this volvox can swim by virtue of their movement. Okay. So, you will see we could get a small video by courtesy Professor Raymond Goldstein. So, you can see the video to see how this volvox can swim. So, this is the volvox, okay, as we have seen. So, these are done in the Cambridge laboratory. So, you can see. So, this is a kind of ball dancing. So, these are moving, there is no external field as such, these are moving by virtue of movement of these hair like structures. Okay. So, that is what is happening. Okay. So, these understanding the mechanism of this is very much important, because in various applications various bacteria can be utilized. So, if you understand the mechanism under which they really migrate and then swim, so one can design some control mechanisms and then so that achieve optimal results. So, that is aim of understanding the mechanics of swimming microorganism. So, also there are other interesting examples we can see. So, the other interesting example is called Paramecium. So, it is an object where you have a ciliated protozoan, okay, and single celled organisms and these are found in fresh water. So, they are covered in cilia, which are like short hair like structures. Okay. So, that is so you can see this. So, these are the so this is entire thing is a single cell, and of course, you have some feeding happens. It is like mouth like a small slit, but the main thing which we are interested is this hair like structure cilia. So, naturally this is able to move without any external forces by virtue of these cilia movement. Okay. So, these are some interesting examples, and there are several such examples. Okay. So, the basic thing is these are moving by virtue of ciliary propulsion. That means, these hair like structures. So, you have a collection and they produce. So, like this. So, it is a rowing like. Okay. So, this is a rowing kind of structure. So, these hair like structures they do like this. So, that is and by virtue of that what you will see, suppose you imagine some hair like, and then you apply some let us say pressure. Okay. Suppose you puff it. So, then you will see all of them are moving like this and then coming back. So, you can see some kind of a wave pattern, because they are attached to the spherical ball, right. So, they are attached to so this is the spherical shape, let us say, and then you have hair like structure. Okay. So, when you there is a life in it. So, therefore, by virtue of that they are moving. So, when they move, what happens? So, you can see some wave like, because they are moving like this, right, and this is called a metacoronal wave. This is called a metacoronal wave. So, basically the microorganisms they are able to move by virtue of this metacoronal wave. Okay. So, what is the envelope model? Embedding these hair like structures by a fictitious surface. Okay. So, that is a instantaneous surface covering the ends of the undulating cilia. So, that is the envelope model, which means if you have the hair like structure. So, then you are depending on the size of the hair like structure. So, we are okay. So, this is the envelope which we are referring, because these hair like structures they are of different size sometimes, and then they are moving. So, sometimes the maximum is here and then minimum height one is here. So, they move like this. So, therefore, here. So, this is the envelope. Okay. So, basically when Lighthill and then John Blake. So, they have tried to model. So, they have introduced this so called envelope model, and then on this surface the movement of these cilia is given in some sense as a surface activity. Okay. So, that will drive the flow. So, we are going to see that, and individual cilia are replaced by a progressive waving envelope. That is what I mentioned. So, there will be a metacoronal wave, and then this wave like envelope. So, that is the progressing wave like envelope. So, that is the model. Yeah. So, you can see the picture from the article by John Blake. So, these are the hair like structures. See, they move. So, here it is moving, it is bending, and it is almost straight. So, by virtue of that you will get some wavy pattern. Okay. And when they are moving, you will see the wave progressing like this, and this fictitious surface which we are trying to cover the ends of the cilia. So, that is the envelope. Okay. And this is the wave structure which you can see. So, for example, you take some threads like this, and then you apply some air, then you will see such. Okay. So, this is a metacoronal wave. So, basically this is driving the motion of the microorganism. Okay. So, already we have mentioned tips of cilia are closely packed during beating and form a continuously deforming surface referred as envelope. Surface distortion is approximated by small amplitude radial and tangential motion on the spherical surface. Okay. What we mean is the entire activity is by virtue of movement of this cilia, which means on this envelope model somehow we have to simulate the movement of cilia. So, this we have to simulate, and this movement of cilia is a surface activity. Okay. So, what we are trying to do in this envelope model is some surface velocity is given, which is simulating this. Okay. So, that is the main aim of the envelope model. Now, it can be very arbitrary, it can be radial as well as tangential, but in general in the so called squirming motion, radial motion of the envelope is neglected and the squirmer is assumed to be propelled only by tangential motion. That means, these hair like structure, so they are not exerting so much movement along radial direction, because they are attached to the surface of this and they are beating. So, as a result, so lot of activity by virtue of the tangential movement, and then it is able to move. So, that is a squirming. So, the basic assumption here is there is no radial activity, and the entire propulsion mechanism is by virtue of a tangential motion on the surface, and even this tangential motion could be arbitrary or axisymmetric. Typically, as a first approximation, this is assumed to be axisymmetric and steady in time. Okay. So, what is the structure of this? We will see. So, this is a approach. So, with this approach, let us start modeling. So, we assume Stokes equations and then the corresponding equation of continuity. Okay. Now, since we are interested in discussing 3-dimensional, and in the previous lecture we discussed already Lam's solution. So, we make use of this, even though I have given introduction starting from Lighthill and Blake's model. So, we slightly deviate when it comes to the actual solution. We discuss Lam's solution and then the corresponding solution mechanism as indicated by other group, Eric Lago, again from Cambridge University. Okay. So, let us consider, we assume that the motion is axisymmetric, therefore, we have only radial and tangential, and we have seen in the previous class for axisymmetric how the Lamb solution gets reduced. Basically, it is expressed only in terms of two scalar harmonics, that is P n and then phi n. There is a curl part chi n, which is basically contributes to the rotation part. Since in this case it is axisymmetric, so that is missing. Okay. So, we take it the Lamb solution, and since it is axisymmetric, you can recall. So, this is the corresponding harmonics, and these are the constants which we have to determine. Okay. Now, you will see how we can determine this. The problem is axisymmetric, but we have two constants, but as I indicated, the entire thing is surface activity which is only in tangential direction. That means, there is no radial activity on the surface. Okay. So, we compute using this, we can compute the corresponding velocities. So, radial and tangential velocities are given, which again involve two constants. As I indicated, the squirmer swims purely by tangential velocity profile, there is no radial surface activity. Therefore, the velocity on the surface is 0. So, this could have been u r. Okay. So, this is 0, and one can refer the work by this for more details on this solution. Okay. So, this one by we force the radial velocity 0 on this, then what we expect? We expect a relation between a n and b n, right. So, u r is forced to 0, then we get a relation between a n and b n. It is very easy, straightforward, one can compute. That means, now one arbitrary constant is reduced. So, this relation will be substituted in these velocity components, then you will see reduced velocity. Okay. So, this is the reduced velocity. Okay. Now, what is the assumption? The assumption is you have a surface activity which is tangential and it should be prescribed, right. That means, you assume this is the organism and this is the viscosity of the fluid in which it is sitting. So, you expect some surface activity. So, that will be given in terms of some tangential activity in terms of some arbitrary coefficients. Suppose you change the fluid, so then naturally the beating structure will change. So, again the corresponding arbitrary coefficients could be different. Suppose you drop a microorganism in a very highly viscous flow, then naturally the cilia beating is almost minimal. So, the coefficient, the surface activity is something. Suppose it is very low viscous, then it will be a fast beating, right. So, correspondingly, so you can see this in various situations. Okay. So, what is the surface activity? Okay. So, radial is 0 and tangential structure of the velocity is this sin theta, and derivative is with respect to the argument of the Legendre, and here the argument is cos theta. So, here the prime denotes the derivative with respect to cos theta, it is not derivative with respect to theta. Okay. So, please make a note of it. So, now the Lighthill and Blake, so they have given such surface activity which is only tangential. You see, even though we have written as velocity vector, only you have a tangential component. Okay. So, radial is 0, that is what we have assumed. Now, the surface activity is controlled by the arbitrary constants B n. If B n is 0, there is no surface activity, and if you keep on changing the values of B n, then the surface activity will be changing. So, that is the understanding. Okay. So, now we are ready to solve the problem. What we are telling is, for a given surface activity B n, how the corresponding spherical particle responds, that is the problem. Okay. Now, the question to be asked is, what drives the flow? Yes, B n drives the flow, because if B n is 0, no surface activity, the sphere will be at rest. Otherwise, you have to give some B n and then obtain the solution. So, how this will be done? So, part 1 is you take a spherical particle moving with say uniform velocity, which is say along z. Okay. So, this is plus a squirming. So, that is due to the tangential surface activity. Okay. So, this is one problem, this is another problem. So, as we have seen in the previous lecture, when you have a particle flowing in a tube, so you have a linear superimposition of the solutions, individual sphere and this one flow inside a tube, and then we have superimposed, because the problem is linear and you can happily superimpose the solutions. So, similar thing we are doing. Suppose there is no cilia, then simple laboratory frame attached to the sphere. So, sphere is migrating with velocity u, and that we are expected to determine. Then if you have a cilia, you have a surface activity by virtue of the beating, and that will generate the squirming motion. So, now we would like to see the combined effect. Okay. So, we would like to solve the problem as two parts, flow past a stationary sphere. Well, when we say stationary sphere, the frame is attached to the sphere. Okay. Then flow past a sphere with some non-zero beating, which is prescribed. Okay. Okay. So, first part we are considering a moving sphere with velocity u along the z direction. As I indicated, we are fixing the frame with the sphere. Therefore, the boundary conditions to be satisfied are the corresponding uniform velocities on the surface. And if one can please recall, we have solved Stokes flow fastest sphere problem using stream function and computed the corresponding velocities. These are exactly this. Okay. Only thing difference is you would have seen these terms before radial and this term before the tangential. Here these are not seen because we have fixed the frame with the sphere. Therefore, the boundary conditions are this, whereas in the earlier case we have taken a far field ambient velocity and no slip condition with 0 velocities on the boundary. Okay. So, hope you understand the difference. So, correspondingly this is Stokes flow past a sphere, then this is the flow past a sphere solution that we have computed, and this is the squirming solution, which is exactly these two, because already we have eliminated one of the arbitrary constants. This is the radial velocity, this is the tangential velocity due to the squirming motion. Then this is flow past a sphere. Now, this is the linear superimposition, this is the flow past a stationary sphere and this is the squirming. Okay. Then we have the combined solution. Okay. So, now what will determine the swimming? Naturally, the surface activity B n. So, these B n's are in some sense strength of the beating cilia. Okay. B n 0, there is no swimming. Okay. It is stationary, no beating, no squirming, and it is only flow past a stationary sphere. So, B n you are increasing the order, you expect more beating. So, in some sense B n's indicate strength of the beating. Okay. So, we expect that u should be depending on B n. Okay. So, that is a general immediate intuition. Okay. So, how do we determine? We do the net force balance. Swimming is nothing but flow due to the stationary sphere. So, that is nothing but the Stokes drag. Then due to the Lamb solution, one can get the corresponding drag. So, please refer this to get the formula of the drag. This is a very the way we have discussed Faxon law using Lamb solution, drag and torque can be expressed in terms of these scalar harmonics. For example, drag is expressed in terms of the scalar harmonic p minus 2. There is no corresponding phi harmonic is coming. So, using Lamb solution, this is the corresponding squirming drag. Okay. Now, we balance the net force, that is force due to swimming plus force due to squirming equal to 0. So, once we do that, this plus this equal to 0, we determine u exclusively in terms of B. That is our intuition. Okay. Which means, so you have a stationary sphere, on top of it you give little bit of cilia. So, B n is something. So, then you expect u is something, some motion. Then you increase more cilia, that means B n is increasing. So, then it is more activity happening, it swims more. Okay. So, that is how the relation is between u n and then the surface activity via the constants B n. Okay. Now, we have obtained the complete solution, because u is determined. Once u is determined, we have the complete solution. Now, keep giving the constants B n's and you estimate the total swimming plus squirming. Okay. Now, let us see typically this is coming from u, right. So, maybe this has some special character, right. So, let us see what happens if one considers exclusively the B 1 mode. So, that is our next. Okay. If somebody considers exclusively the B 1 mode, this is only swimming, that means there is no no contribution of the squirming, okay, the envelope and then the surface beating, it is only swimming. And again I apologize for introducing this term potential dipole, because these are singular solutions, the details we discuss later. Okay. For the time being, you understand that when we say a source, a sink, a dipole, etc., these are singular solutions. Okay. What are they? Details we learn. So, the mode B1 is corresponding to swimming, and it gives, this is the complete velocity. How we are getting this? This times ER plus this times E theta, that is a okay. Now, if one plots a vector plot of just this mode alone, this I have directly taken from this work, you can see beautiful explanation of this. As I indicated, this is on its own a nice research problem. So, we will not be able to summarize the complete physics. For details, one may refer this work. So, for positive B1, this indicates swimming upward. Okay. It is only by virtue of u it is happening. So, it is swimming upward, no squirming happening, right. Then the mode B2. So, this is a solution due to B2. Okay. Now, B2 positive is shown in the left, B2 negative is shown in the right. So, you will see here there is no swimming, only the corresponding squirming is happening. This is positive, and then so if it is positive, you will see the flow is it is released, okay, along the direction and behind, and from sideways it is pulling, and if it is negative, that is B2 negative is this side. So, along it is flow is pulling, and sideways it is pushing. Okay. So, this has a corresponding structure in it. Now, the combined is plotted. So, that is this is a swimming where B1 is -1 and B2 plus or minus 4. So, here it is negative and here it is positive. So, now correspondingly you will see here pusher. So, this is a swimming direction, that means in both case it is swimming, but there is a big difference. Pusher means it is like, so when you do this, okay, this stroke, so the flow along the direction, that means forward and backward it is pushed and it is collected from sideways. So, that is what is happening, it is collected from, due to axisymmetry only one portion is shown. If you plot other, say other direction also, it would have come. So, it is collecting from sideways, whereas polar it is pulling. So, along the direction front and back flow is collected and flow is pushed sideways, that is what is happening. So, this is a pusher and puller activity, and as I indicated, so the complete physical explanation and all the modes corresponding structure is nicely explained. Okay. So, this gives idea about swimming microorganisms and how the corresponding mechanism. As I indicated, this is very elementary problem. More complicated is arbitrary swimming activity and then time dependent activity, okay, and sometimes as a function of viscosity, the surface activity is as a function of viscosity. So, these are some complicated, lot of literature available. So, I would like to draw your attention to more interesting microorganisms like spermatozoa. So, the problem with this is it is not regular shape. So, the aspect ratios are very nasty, and moreover there is a hair like structure. So, how one would estimate the swimming structure of this? So, for this typically boundary integral methods are more useful, because you have a head like structure and tail like. So, people go for corresponding singular solutions and distribute on the surface of the head and also on the surface of the tail, and lot of work has been done. For example, the group of John Blake at the University of Birmingham and Dave G. S. Smith at University of Birmingham, they have done lot of work on moving Spandau Java. So, with this it is analytical. The first problem that we have shown is very analytical, and one can really do the algebra and then feel it, but the more complicated, like the Spandau Java that I have shown just now, then the calculations becomes very nasty if you would like to attempt using analytical. So, therefore, one has to go for really numerical computations. Okay. So, I hope you enjoy this, gives a flavor of how to model transport of microparticles. Thank you.